it going, everyone? Mr. Geyser here with the first video in our Lesson 12B series, where we'll be exploring these logarithmic function manipulations in a little bit more depth. In those last videos, in that fourth example, we explored some manipulation where we showcased that a horizontal dilation really was just a vertical translation of some kind. In this example here, when graphing these functions here, we want to try and showcase that on this grid. Where in example 5, we're given g of x is equal to the log base 2 of x squared for any x value that's positive. If we really do plug in negative x values, we can't really have negative x values for logs, so we do need to specify that we're only looking at the positive x values here. In part A, we want to use the power property to show this as a vertical dilation of the function f of x is equal to log base 2 of x. Well, first thing first, we're going to plot that f of x function yet again, where we're able to plot these 3 points exactly. Again, these 3 points come from the fact that we're using a base log. That base log here is base 2. That very first point of 1, 0 is always given to log bases. That second point is coming from the fact that it's 1 over the base, comma, negative 1. In this case, we have 1 over 2, comma, negative 1. That third and final point that we know for all of these bases is going to be base, comma, 1. And in this case, we have 2, comma, 1. Those 3 points we always know we can plot for these kind of logs here. We can extrapolate that information and get some other points later on. But really, I want you to spot those 3 points in all of these graphs today. Let's clear that up and just graph our f of x function here, where for our f of x function, we're just showcasing that it's going up in this right direction. And let's try and expand out our g of x. For g of x here, we're given log base 2 of x squared. First, let's just pull out that 2 from our x squared and bring it into that product of 2 times log base 2 of x. And we can kind of see this vertical dilation on our function here. We have some value multiplying the product of our equation. So with this here, we're given our g of x, and I want you to see these 4 points here on our graph get affected. We know that for every point being plugged into our parent function and this, or into parent function, those y values are going to be something multiplied by 2. What happens is that all of these values here get stretched vertically on our graph. In general, for this first case here, from this point to this point, what we're really doing is we're taking that x value of 1/2, comma, negative 1, and we're just multiplying the y to get that g of x of 1/2, comma, negative 2. In example 2, nothing really changes. Our y value is 0, so we just get that same x-intercept of 1, 0. In example 3 and 4, we can start seeing this effect more prominently, where our original point for f of x was 2, 1 and 4, 2. Our new 2 points for g of x here is 2, 2, 1 times 2, and 4, 4, 2 times 2. It's those y values that are being stretched. So when we're graphing this, notice how the top of the graph is actually going higher above our f of x, and the bottom of the graph is kind of getting pulled in a little bit when it gets stretched in this vertical fashion here. In part C, when we want to describe the change in the output values over an equal length input value intervals, what we're really trying to get at here is that as x increases 1 unit, the y values of the child function, g of x, experience a vertical dilation of a factor of 2. This 2 here comes from this 2 multiplying our log function. I'm going to push that over real quick and then try and make this transformation rule. That transformation rule really is just that f of x, or x, y, is being transformed into g of x by saying x, 2y. Now, let's explore our example 6. For example 6 here, we're given that g of x is equal to log base 2 of x minus 1. In part A, we want to use the change in base properties, that log base b of x, which is equal to log of ax divided by log of ab. We're going to use that property there where a is larger than 0, it's not equal to 1, to show that this vertical dilation of f of x for log base 2 of x really does have a pattern between all the logs that we can see. Notice this. We're given f of x here, right? We have this base function here that we're very familiar with. If we write down f of x, it really just is log base 2 of x. What we're really trying to say when we're using that property here, that change in base property, is log base 10, common log, of x divided by log base 10 of 2, that original base there. Well, what we're really saying here, if we expand out that fraction, is just 1 over log base 10 of 2 times log base 10 of x. Between these two steps here, that's just a normal fraction property where you're taking this multiple of 1 over log base 10 of 2 times log base 10 of x. But I want you to notice that every single log base is just some vertical dilation of our common log. If we had a log base 20 of x, this would be 1 over log base 10 of 20 times log base 10, where this here is just some vertical dilation. So that means that all base log functions are vertical dilations of each other. Every single one of them are just some vertical dilation of each other. It's a cool pattern. And we can showcase this with g of x, where g of x here has that log base of 2. However, it also has a horizontal translation, where if we have anything affecting the inside of our log function here, it's going to cause some horizontal translation, not a vertical translation or vertical dilation. For this function here, we're just moving that function over to the side, and we can express and describe that g of x as x increases by 1 unit, the y value of the child function g of x experiences a horizontal translation of 1 unit to the right. I'm going to push that over to the side real quick. I'm just going to write that rule out for g of x, where g of x is just a transformation rule where f of x, x comma y, is equal to g of x, x plus 1 of y. For g of x here does not follow this vertical dilation because it has a horizontal translation affecting it. Any log base that has this common log, log base b of x, that common format, is just a vertical dilation of our common log base of 10x. Thank you very much for joining me on this exploration in example 5 and example 6. And I look forward to seeing all of you guys in that next video. Take care.